equation such as this. Y is equal to x squared, right? And then we still have to have something called the initial condition. Let's say when x is equal to 0, y is equal to -1. Let's just think about this, just so that you get a taste of what differential equation is. So y is equal to x. See, screw up right off the bat. What I meant to say was dy over dx is equal to x, right? So we have some kind of derivative and some kind of x and y, but in this case, it just has x, so that makes it easier. How do we solve such a thing? Well, we anti-differentiate both sides, or anti-derivative both sides, right? So y, this thing becomes y then. What does this become, right? Well, this thing, I think I need to write this and give you a notation. What? Are we missing limits of integration? Yes, we are. Right? Usually in this, a, b, right? And then it becomes a constant when we evaluate it, unless you put x up here and make it an integral function. My favorite. You see how much I like integral functions on this test, right? However, Leibniz, because we didn't have any good notation for antiderivative, right? Leibniz come back again for us. See, we know, according to fundamental theorem, antiderivative and integral are the same thing. So when we lose this a and b, this technical term is called indefinite integral, as opposed to a and b, that's called definite integral. I know mathematicians love to create new vocab for the same meaning. We are just using this as an antiderivative symbol, okay? So if I don't have this a and b limits of integration, then it just means between this symbol and that symbol, find the antiderivative of that thingy. Very good? Okay, so y is equal to now 1/3 of x cubed and then plus ca. Now, how do we, well, figure out what that's? See, that's when this initial condition comes in handy, okay? So if we plug in 0, -1, what we have is y becomes -1, x is 0, so that's c. Aha, we figured out what c is, so therefore y is equal to 1/3 x squared minus 1. You get it? So let's review. Solutions to the differential equation must satisfy this. Let's check. If I differentiate it, dy over dx is equal to x squared, and this one, -1 dies. It also must satisfy this. So once I plug in 0 here, y becomes -1. That's good as well. This is called the differential equation. Now, this part right here is known as the general solution. Riley.
Should it be 1/3 x cubed?
Oh my God. Particular solution. Yes, nice catch. This is cube and I wrote square here, huh? Cube. Good. So this is general format of differential equation. I mean, not that you would know how to do this, but now I'm going to give you the formal way before I do something next, which is not as obvious. Okay. So now,
so Kim, what does the initial condition represent? Like a point, or?
Do you remember on a slope field we can have so many different families of curves?
Yeah.
Depending on where that initial condition is, then we can approximate the curve where this curve goes.
Mm-hmm.
So this can be any constant. So do you see a bunch of the families of curve that looks like this potentially?
Yeah.
Right. So once you have, and then let's say this is 0, -1. Right. Once you put that one, then you say, it's this one. You get it?
Mm-hmm.
So when we say general solution, it means all of these, right? It differs by constant. That was an excellent question. And particular solution means that one and that one only and nothing else. How about that?
Thank you.
Wow, that was actually an excellent question. A lot of people benefited from this video, so I need to use this video and save it, despite of my mistake here. Okay, but at least you guys caught it. Okay, now let's look at the next differential equation that you might say is a little weird. Somebody keep track of time. So we don't have a whole lot. dy over dx. Now, I don't know why I'm so anal. dy over dx is equal to y. What? And then let's use same initial condition. And right off the bat, how do you integrate that thing? Like, what? Why? This y messes you up. See, on this, once it is the mixture of the derivative dy over dx, and you have any combination of x and y, and we have seen that on slope field and Euler's method before, right? How are you gonna do this? First, guess and check. And German word for that guess is called Ansatz. Whatever, some professors will use it. So guess and check is a pretty valid technique in math, especially differential equation, which is a 2-semester course. I know this alone is 2-semester course, and that's scary. Okay, do you know any function that you can take a derivative and get that function back? Do we know anything like that? And quickly, give me the answer.
E to the x.
E to the x, of course, right? Because if you take a derivative, then we pick up e to the x. Oh, at least we satisfy this. But we don't satisfy this. And then where do we put the constancy? One might say like that, right? But you see that screws up, because if you take a derivative, it's not exactly the same thing, because this constant dies, so that no longer satisfies that. So where does that constant go? Is my first question. And what is that constant? And the key here is you put the constant here. What? Why? We can check. Let's check. dy over dx. What is it? C times e to the x. Oh, so at least it satisfies this, right? So we have to satisfy this. And so this is a general solution. And that's a little weird. Why, instead of adding constant, why would you put it here? You know what I'm saying? So at 0, -1, so you plug in 0 here and -1 here. So -1 is equal to C, and that becomes, oh, it worked. So therefore, y is equal to -e to the x is our particular solution. How about that? Yeah, but that defies all logic, and there's got to be a systematic way to do this instead of guess and check. You know what I'm saying? Although that is crucial thing. So let's do it more systematically, okay? So I'm gonna go back and start with this differential equation is equal to y, and this is one of the most basic one. Okay, and watch this. This is known as the title. Our title is separable differential equation. In high school level, we only deal with separable differential equations. Okay. So what we do is we separate y on the left-hand side and x on the right-hand side. How's that? I mean, like, yeah, we have seen something similar before when we did the chain rule. So I guess not that difficult to swallow, eh? And then what we do is, you get it? And we don't have to really draw it. I'm just drawing it for teaching purpose. We just go on to the next line. So this is, I think of it as 1 over y and dy here. You get it? So what is the antiderivative of 1 over y? Feel free to use your microphone. What is the antiderivative of 1 over y?
Natural log of y.
Ooh, are you sure? Because once you write ln, now there's a negative 10-point penalty potentially. So unless you're sure, don't write it. But are you sure? Yes, we are, right? This is just 1 over y, first power. So yes, it is. Okay. And the other side, what is this thing? Well, there's a 1 here. So antiderivative of 1, what is it? X. You get it? See, this has dy, so we get some expression of y. This has dx in it, so we get some expression of x. You see what's going on? And then tell me what I forgot.
Plus c.
Plus c, this is the most common mistake. See, on the AP grading guideline, if you forget c at this point, it's 50%. You stop right there. You only get 50% at most, sometimes 40%, sometimes 30%. I mean, they explicitly say without C, only 1 point. This is a big deal. Okay, so for doing on time, 25. I think we can finish it. So far, so good. Now,
You plus c on the right side and not on the
oh
left.
yeah, oh, that's another excellent question. Wow, this class. Yeah, let's add it. But you see, that's a problem, right? Then the C cancels, so D, how's that? So far, so good? But wait a minute. That's just same thing as then this, isn't it? But then these are, both of them are constant. Can we just combine it into one? Oh yeah, that's why we only put it in one side. You get it? So they're really there. Oh, on a side note, because this is kind of important, you remember this, right? From Algebra 1. You all allegedly got an A. Kara, do you have a question?
Oh yeah, so when you were doing dy over y, how come you were just like finding the antiderivative of 1 over y?
Do you see this is exactly same expression as that?
Oh yeah. Oh, okay.
Yeah, okay. So that's why. No, these are other people will benefit from your questions, okay? You guys are excellent today. I don't give compliments easily, in case you haven't noticed that. I mean, I sometimes give backhanded compliment. Okay. Obviously, right? How come we don't put plus or minus here? Why are we discriminating? Shouldn't we be all equal to everybody, exactly equally in this political correctness environment, woke culture? Why is it not there? Watch, it's really there, it's just redundant. The only combination is this, right? Do we get 4 different possibilities? No, we only get 2, right? This just tells you x is equal to -2, and this is x is 2, and this also tells you x is equal. You see, they're all there. But it's redundant, so we only put it. Either they are the same sign or they're opposite sign. That's all this plus or minus means. You know what I'm saying? So we only put it on the right-hand side because we want to have x is equal to. Same thing here. That constant is really on both sides, but we combine it to one side. You get it? And we want to have it on that side because we want to say y is equal to, our solution in this case, y is equal to function of x. Good? Now we have to apply the initial condition. So at 0, -1, what we have is, this is supposed to be -1, right? So do we have ln? That's why absolute value is there, by the way, how convenient. That's equal to c, eh? So what's our c? Our c is equal to 0. So far, so good? Okay. So c is equal to 0. Now, then we go back and say ln y, absolute value y is x. Now we still have to solve for this y, right? So absolute value of y is equal to e to the xa. Now then y is equal to plus or minus e to the xa. Wait a minute, plus or minus e to the x, it represents this curve as well as this curve, right? Which one is it?
-1.
-1. How do you know it's a -1?
Because y is -1.
Well, yeah, initial value, that one, bang, that one picks this one, right? And not that one. I'm saying, so initial value comes into play again. So what we have is y is equal to negative e to the x. You get it? So we are using this initial value twice, here to figure out c and here to figure out the sign. You have to pick one. You cannot have both. Okay? Particular solution means one solution. Then you're thinking there's gotta be a better way, right? And there is. There is even better way. I did it this way to just show you what's going on, but there's a shortcut. So here comes the shortcut. Okay? I'm going to put it over here on the side, alternative. Okay, here's an alternative. Now let's change the color. What color do you want? Red. Alternative.
Oh.
Okay, yes.
Oh,
I'm
sorry, I said purple, but you can ignore me. It's okay.
Okay, I'm gonna pick it up right here, right? So y, ln y, and let's do that. See, when you're in a hurry, ln absolute value y is equal to x plus c, right? We just solve for y, right? You know what I'm saying? Okay, and then y is equal to plus or minus e to the x plus c, correct? Well, isn't that the same thing because we have to pick c and we have to pick sign, right? Not so fast. This is same thing as plus or minus e to the c e to the x, rule of exponents, eh? Now I'm going to say this y is equal to, you notice that this whole thing is a constant now, isn't it? Let's call this another constant, a or b or giant C. And then you know what I'm saying? They are constant, right? And watch. Now I apply initial condition. So if I do that,
X.
yes. Huh?
Did you mean to write e to the x for
This,
y?
no, e to the c. This
No,
whole
no,
thing.
next to it. To the left.
No, oh, this. Yes, I do. Yes, I did. Okay, good. Now then, y should be -1 and x is 0, which means this whole thing is 1. So a is -1. Huh, bang, one shot. You know what I'm saying? We didn't have to apply initial condition twice, just one will do the job here. So y is equal to -e to the x is our final answer. So this is the most recommended way. You get it? Any other excellent question? Okay, we'll do quickly one more, and this time we'll do it the best way alone, okay? So the next example I have is this. This it will just make, it looks intimidating, but it's really not. Okay, let's separate it. You see, it's not that intimidating, and once again, you don't have to put this symbol. I'm just putting it so that you know what's going on. So on the left-hand side, I have ln absolute value of y again, and we are sure. And the right-hand side, we are going to have x squared, therefore 1/2, and plus c. Still with me? That means absolute value of y is equal to e to the 1/2 x squared plus c. Okay, continuing up here, that means y is equal to plus or minus. Now we know, we have seen this script before. We just separated, use the rule of exponents to go from here to here, right? And then that thing is my a, you get it? I'm gonna color code it. This is my a. Okay. So now my y is equal to a e to the 1/2 x squared, and then my a here is plus or minus e to the c, 8. Okay, then initial condition 0, 1 this time. So y becomes 1 and x is 0, so that makes this whole exponential thingy 1. So we have, oh, a is equal to 1. How nice, right? So therefore, y is equal to e to the x squared over 2. Huh, aren't they beautiful? Okay, these are separable differential equations. Any questions? Ethan?
Yeah, what would constitute an inseparable differential equation?
Okay, inseparable differential equation. Lots of good questions today. You remember this guy? I mean, you can try to separate it, but it's not easy. How do you separate this thing? I mean, that's something that simple. Usually the multiplication is good, pluses and minuses are bad in math. You know what I'm saying? So you cannot separate that. So that's inseparable differential equation. And here's an even better one. Well, that's like kind of separated. No, it's not, because it has a dx in the denominator. And the second, oh my God, this is known as a second degree differential equation. Like, okay, you're not going to see this until a year and a half later, okay? So it's like, okay, let's not scare children like that. Okay, Ava.
Wait, can you go up in the notes? Because I have a question about the previous notes.
This one?
A little bit higher up.
This one?
The one in red, why did you choose e to the x?
This one?
Yeah, that one.
Okay. See, it's just a guess and check. Do we know any function once you take a derivative? It's a function itself. Or that's the exponential function now, isn't it? This is not a recommended way. This is a motivation. This is the beginning basic differential equation of all. So I wanted to give that motivation. I once had a professor, he always goes through history and historic motivation of the theory and the definition. These things all have a motivation, the reason we started studying this.